Assalamualaikum everyone. So today our group would like to present our final year project presentation on using graph theory to determine boiling point, flash point and refractive index formula for alkanes. First of all, we have three group members. One, me, Muhammad Nabil, and we also have Sharina Azwani and Nurul Hidayah binti Khairi. In this video, we're going to talk about the abstract, introduction, literature review, methodology, results and analysis, discussion, conclusion, and references.
The use of the Harari index in the quantitative structure property relationships is exemplified in the modeling physical properties of the alkanes. In this application, the performance of the Harari index is comparable to the performance of the Wiener number. Here we report our findings of 24 chemical compounds using Harari index, along with flash point and refractive index. The flash point is a general indication of the flammability or combustionability of a liquid. Below the flash point, insufficient vapor is available to support combustion. At some temperature above the flash point, the liquid will produce enough vapor to support combustion. Furthermore, index of refraction, measure of the bending of a ray of light when passing from one medium into another. In the context of how this study would actually benefit students can use graph theory to estimate the physical properties of alkanes. Example for ethane, like the boiling point, refractive index, and flash point of the compounds. On the other hand, society could benefit from graph theory as a stepping stone to further study on a more advanced of scope on the same topic. At the very least, society could take it as a general knowledge on chemistry. The numerical invariants of chemical graphs are increasingly being used for a single number characterization of the corresponding chemical compounds. These invariants are named in the chemical literature as topological indices or graph theoretical indices. Topological indices have found application in various areas of chemistry, physics, mathematics, informatics, and biology, but their most important use to date is in the non-empirical quantitative structure property relationships and quantitative structure activity relationships. Graph theory is used to mathematically model molecules in order to gain insight into the physical properties of these chemical compounds. Some physical properties, such as the boiling point, are related to the geometrical structure of the compound. This is especially true in the case of chemical compounds known as alkanes. Harari index is another kind of graph invariance for the graph characterization of molecular graphs. The Harari index is defined as sum of reciprocals of distances between all pairs of vertices of the graph. All graphs shown in this research paper is finite and simple.
In the context of determining the physical properties of molecules, graph theory is very useful in modeling the molecules. The atoms of molecules are mapped by its vertices and the bonds are represented by its edges. The hydrogen atom, however, are removed from the graph since each carbon are tied to 4 bonds and hydrogen atom have 1 bond each. Therefore, no valuable information can change the desired value is altered by doing so. The reason why hydrogen atoms are removed is to simplify the chemical structure in calculating the carbon-carbon distance. Since the alkene study contains no cycle, the path between any pair of vertices was chosen in a way that is always the shortest between two vertices. The branching of molecule structures, however, was chosen randomly as the matrix would eventually total up to the same value. After calculating the carbon distance, The reciprocals of each value were obtained, summed up, and divided by 2. This gives a Harari index of one molecule. Harari index of molecules increases along with the number of carbon atoms. With a complete set of Harari index molecules, graph of boiling point against Harari index, graph of refractive index against Harari index, and graph of flash point against Harari index were plotted with the help of Microsoft Excel. There is a linear relationship between the dependent variable and independent variable for all the three graphs. For example, graph of boiling point against Harari index, the boiling point increases along with the Harari index. However, the plot points are somewhat clustered, suggesting that the number of carbon atoms play a role in correlation of x and y in the graph. The R2 value of the graph shows an accountancy for much of the mean of the dependent variable from the identified independent variable. This is because the R2 value obtained are at 0.93. On the other hand, the graph of flash points against Harari index shows bigger cluster among the plot points. This is expected, as flash points cannot be applied in itself, as the technique used can produce different products. Flash points also vary between countries. Lastly, the refractive index relationship with molecules is the same as the Harari index, with both values increasing with an increase in the number of carbon atoms. Therefore, the graphs obtained can be used to determine the physical properties of molecules, with no experimental data available prior to the study. For the methodology, the project started by constructing the chemical structure of every chemical compound listed. Secondly, the boiling point, refractive index, and the flash point were determined with the use of Wikipedia. A table containing the chemical name, the chemical structure, boiling point, flash point, and the refractive index was created. After that, the Harari index for every chemical compound were calculated, and the values obtained were recorded in the same table as before. From the values obtained, three graphs were plotted. The graphs are graph of boiling point against Harari index, refractive index against Harari index, and flash points against Harari index. The graphs were plotted using Microsoft Excel. The linear regression method was obtained through Microsoft Excel by highlighting the data and selecting the trend line along with the extra options in the Chart Tools menu. From the graph that has been plotted, the formula of boiling point, refractive index, and flash point were determined. This is the result for the Harari index of butane. So to calculate the Harari index, first you number the carbon atom 1, 2, 3, and 4, and then you create a table where in the first row and the first column you number it 1, 2, 3, and 4, and then you calculate the bond between the carbon. For the first carbon, carbon 1 and carbon 1, there is no bond in between, so it is equals to 0. For carbon 1 to carbon 2, there is one bond in between. For carbon 1 to carbon 3, there is 2 bonds in between, and carbon 1 to carbon 4, there is 3 bonds in between. And then you create another table where the values you obtain from the first table, you change it into reciprocal. For example, the first one, 1 over 0, you will get 0. Second one is 1 over 1, you will get 1. The third one is 1 over 2, you'll get 0.5, and the last one is 1 over 3, you will get 0.33. And then you sum up these 4 values and you will get 1.83. And then you continue with the rest of the values, and then you summed up the reciprocals value, and then you divided it by 2 using this formula. 8.66 divided by 2 is equals to 4.33. So moving on to the next slide is the table containing chemical name, chemical structure, boiling point, flash point, refractive index, and Harari index of the 24 molecules. from the table before, you will plot a graph of boiling point against Harari index. The formula obtained for the boiling point is y equals to 12.192x minus 55.25, and the r-square value for the boiling point against Harari index is 0.9296. The second graph is graph of refractive index against Harari index. The formula obtained for the refractive index is y equals to 0.0058x plus 1.3179, and the r-square value is 0.8541. The last graph is graph of flash points against Harari index, and the formula for the flash point obtained is y equals to 7.0912 0.921x minus 88.579, and the r-square value is 0.7181.
For our discussion segment, I'm going to talk about three graph findings, which are the boiling point versus Harari index graph, flash point versus Harari index graph, and refractive index versus Harari index graph. Common thing in all three graphs is that the pattern is linear with direct proportion between the independent variable and the dependent variable. However, they all have slight differences. For example, in the first graph of boiling point versus Harari index, the plot points are somewhat more organized, with the r-square value being more than 0.9. The plot points are clustered as the molecules tend to have close boiling points. The obvious gap that we can see between the plot points clusters is because of the increased number of carbon atoms. For the second graph, which is the flash point versus the Harari index graph, the plot points are more random. This means that the square of regression is not as high as the previous graph at 0.72. Therefore, the flash points are more random. There is an explanation for this. Flash points cannot be reproduced in the same way effectively because of the various techniques used. Also, different countries have different flash points measurements, which might be slightly different from our findings. In the third graph, the plot points show a similar pattern towards the first graph. All the points are clustered and show direct proportional relationships between the dependent and independent variable. The r-square value for this graph is 0.85. And also, there's one more thing in common between these three graphs. The multiple r value of all three graphs is bigger than 0.83, which is a good sign, as good multiple r is always closer to 1. In conclusion, the concept of graph theory is initially used in mathematical problems. However, its application has expanded to many other areas such as chemistry, social sciences, and operations research. In extended abstract, the graph theory has been used to study the physical properties of chemical compounds such as the boiling point, flash point, and refractive index, and its correlation to the Harari index by modeling molecules. Harari index models the fact that closer atoms influence each other greatly more than the atoms that are far apart in a molecule. The formula for the Harari index having n vertices is given by the boiling point formula for alkanes obtained through the graph is y equals 12.192x minus 55.25. The boiling point formula for alkanes obtained through the graph is y equals 12.192x minus 55.25. The refractive index formula obtained to the graph is y equals to 0.0058x plus 1.3179. The references that we use in our research are